Hey everyone, welcome back to another flip lesson in our relations and functions unit. Today we're going to be talking about determining the inverses of functions, both algebraically and graphically. So with that said, we're going to start with the algebraic approach. But before we do, we want to talk a little bit about what we mean by an inverse of a function. In order to create the inverse of a function, very simply, we are going to take the domain values, which as we know are our x's, and simply switch them with all the range values, aka our y values. All right, so simple enough. We're going to take x and y and literally switch the two in order to create the inverse function that we need. Now, for those of you that were geometry savvy, what's kind of cool here, and we're going to come back to this when we work graphically, is that what we are actually doing is a reflection in the y equals x line. And for those of you that do not remember, just a quick little reminder, here is a quick sketch of our x and y axes. The y equals x line is that invisible diagonal that cuts through all points of equal x and y coordinates. So we have 1, 1, 2, 2, 3, 3, 0, 0, and so on in both directions. And what we're going to do graphically is actually create a reflection over that diagonal line. But before we get there, we want to discuss our algebraic approach. So here's how this is going to work. Basically, in order to create the inverse, we are going to literally take the x and y variables and switch them in their locations. Once we do that, our goal is then to get the y variable in its new spot isolated. And I'll show you that in a second. Before we get there, though, we would need to make note of what inverse notation looks like. So if you take a look here, we see basically our function notation. And then we see what looks like an exponent of a -1. But in this case, that notation designates that we are looking for the inverse of our function. And as soon as we see that, that's our clue for switching our domain and ranges and then solving for the new y location accordingly. So to show you a couple of examples, here's the idea. To take care of the inverse, so if we want to solve for these inverses, first thing we're going to do is anything that is in function notation, we want to rewrite as y equals. And the reason being is that we want to designate ranges as the y, as we've spoken about before. Now, to get this inverse, we're going to take this y value, this x value, and literally switch their places. So we create what looks like the following equation. And now we've begun to find the inverse. We're just getting started here. So now we're looking at the inverse. But unfortunately, we're not done. The y value needs to be isolated. As we know, all functions need to be in y equals form or in function notation form. So all we're going to do is solve for y accordingly. So we get x minus 4 equals 3y. Divide both sides by 3. And in this case, we get our y by itself. But to properly do this, we want to rewrite our answer in its inverse notation form. Since they gave us function notation, we're going to use inverse notation form. And simple enough, we have the inverse just like that. All right? So that's all there is to it. To find the inverse, switch x and y, and get that new y value isolated by itself. One more. In taking a look at our guy here in number 2, we have x and y there, so we're just going to literally take the two values and switch them up, leaving us with x equals the cube root of y minus 4. But again, at this point, our ultimate goal is to get this y isolated. So the opposite of a cube root is to cube. Is its inverse operation. But what we do to one side of the equation, we do to the other, as we know, leaving us with x cubed equals y minus 4. Add the 4 to both sides, and we are left with the inverse notation of our original cube root function. And there it is, guys. That's all there is to it. Switch x and y and isolate the y value. Now, in terms of graphing, basically what we're going to do here is a similar concept. The only difference being we're literally going to have an x and y value set to flip-flop. So for instance, in taking a look at this example, we have our function of a basic parabola, our y equals x squared, and we're going to go into our calculator as we've done before, type in our x squared, and get our table of values in order to graph. So as we've done in class before, looking for our nice pattern, and we're going to take that table and simply recopy it to utilize for the graph. Right? So I will plot these up, and then we'll talk about how we create the inverse. All right, so now that we have our original parabola down, what we want to then do is basically take these two tables of values and literally just flip-flop them. So for the inverse of our function, if we're going to look at our inverse here, we're going to take the x and y table and just switch them. So what was once a y now becomes an x, and so on down the list. Fix that guy for you. So we get 4, 2, and lastly, going a little bit below here, are 9, 3. And again, guys, what we're going to wind up doing is just plotting those points as best we can, and hopefully we will see the inverse develop itself. So I will do that, and then we'll take a look at the relationship that we see. All right, so now with our new list of points plotted, you guys can see visually that we've created that inverse function. And what we want to talk about here, or the inverse of the function, I should say, and what we want to talk about here visually is how we have that diagonal line of y equals x, and how, if you remember from your past geometry experiences, we are literally doing that diagonal flip, that linear reflection across that y equals x line, and that's how we create our inverses visually. So to cap it up one more time, guys, in looking at inverses algebraically, basically we're going to get our function into its y equals form, take the x and y, switch their locations, and isolate the y value in its new spot, noticing that we have a new type of notation that designates inverse, so you see it there. And then from a graphing perspective, we're going to take our original set of x and y coordinates that create the original function, as you see in green, switch them, literally switch x and y to create the inverse function, which acts as a reflection in the y equals x line. With all that said, we'll take a look at this more tomorrow in class. We're going to add some new vocabulary terms in class as well in talking about the relationship between original function and its inverse, and we'll practice this in class together. Hope you guys enjoy the rest of your night, and see you tomorrow for more.